This is the first section of chapter 7 in the pure year 2 book, and it's on addition formulae. So we've got some identities here. You know there are identities because of the 3 lines here. Equivalent sign, which basically means whatever angle you use, these statements are always true. So we've already got some identities from year 1. So we've already got that sine over cos is equivalent to tan for any angle. We've also got that sine squared plus cos squared is equivalent to 1, and we got some new ones from chapter 6, I think it was, where you use second cosec. Now these identities are to do with angles. There seems to be a lot of them, and it seems to be quite confusing at first. They're easy to remember, and actually we can summarize these 6 into 3. So let's start with the sine one. So sine A plus B, or it could be A minus B. Yeah, so I'm going to combine 2 into 1. So if I have the sine of an angle plus another angle, then that will always give me the sine of the first angle times the cos of the second angle plus the cos of the first angle plus the sine of the second angle. And if I have the sine of an angle subtract another angle, then this becomes subtract as well. So I've combined 2 into 1. So you need to think of it like 2 rows of identity. So the top row has a plus on the left hand side and a plus on the right hand side, and the bottom one says, right, when you have a negative on the left hand side, you'll have a negative or a minus on the right hand side. So that's cos. Do the same, sorry, that's sine. Let's do the same for cos. So cos A plus or minus B is always equivalent to cos A cos B minus plus sine A sine B. Now notice on this that although there's a plus at the top and a minus at the bottom here, it's the opposite way around here. And the reason for that is that if you're doing cos A plus B, then you'll actually have cos A cos B minus sine A sine B. And when you have a negative on this side, cos A minus B over here, you will have a plus there. So the sign is reversed on the other side. Then the last one is tan. So tan A plus or minus B, use the same format again. So we'll have tan A tan B plus minus, depending on whether we've got plus minus on the left hand side, and then we'll have 1 minus plus tan A times by tan B. Okay, so when we have a plus sign on the left hand side, on the right hand side we'll have a plus at the top and a minus at the bottom, and if we have a minus on the left hand side, we will have a minus at the top and a plus at the bottom. Okay, so just be aware of that. So these are 3 new identities which we can use to solve equations, simplify expressions, and to prove identities. Okay, so we've got quite a few now, so adding the ones that we've learnt from year 2 as well, we've also got that cos over sine is cot. We've also got 1 over sine is cosec. We have 1 over cos is sec. and then we have 1 plus tan squared sec squared, and 1 plus cot squared is cosec squared. So lots of identities. We could be asked to use any of those. So 6 more or 3 more identities which we're going to use. Okay, this one here is asking us to prove what I call these addition formulae. Now, you don't need to reproduce this into the exam. It's useful to understand how it works, but you don't need to prove sine A plus B or cos A plus B or tan A plus B. But it's useful to see how these are generated. So we've got this complicated looking diagram here, and we're going to use it to help us prove these identities. Right, and I've put here, remember what we know from mechanics. Well, from mechanics, hopefully you'll remember, if I've got a right angle triangle, and let's say that I've got an angle here of theta, and let's say that that represented a force there of F, then the length of this side would be F sine theta, hypotenuse times sine theta, and this side would be F cos theta, hypotenuse times cos theta. So this is going to be useful to help us find some of the missing sides in this diagrams, because I see lots of different right angle triangles. Okay, so let's start with triangle AEC, triangle AEC, this one here, and I can see that the hypotenuse is 1, and I'm going to work out the length of this side and the length of this side. So using what we know from mechanics, the length of AC, and I'll write it on the diagram, is going to be cos beta times 1, or 1 times cos beta. So the length of this side here is cos beta, and the length of CE or EC is going to be 1 times sine theta. So this side is going to be sine beta. Okay, what we're actually trying to aim for is, in this triangle here, we want to know the lengths of this side, and we want to know the length of this side here, because then I can say, right, the sine of this is going to be this length over 1, the opposite over the hypotenuse, and the cos of this angle is going to be this length over 1. Okay, and then I'll get my identity. So I basically want to work out what's the length of DE and what's the length of AD, and I'm sort of working my way towards that. Right, there's a bit more work to do. Right, so if I look at triangle ACB now, ACB, I've got the length of the hypotenuse, I've got the length of, or I know the angle in ACB, so hypotenuse times cos alpha is the length of A to B. So I'm looking at this triangle here, ACB. So let's write that down. So AB is equal to the hypotenuse, which is cos beta, times by the cosine of that angle. So this is the length of all of that. And this side here, I may or may not need it, but I'll work it out anyway. This is going to be the sine, actually let's write it the other way around, it's going to be the hypotenuse cos beta times the sine of that angle alpha. So that's going to be this bit here. Okay, so I've actually found the length from there to there, from E to D. So I've got that bit. I now want to find the length of, like the bit at the top. I want to work out how long is this bit here. Okay, and then in a minute I'll probably be able to find the length of this bit here if I can work out the length of this bit, right? Z angles. Using my Z angles, this angle here is alpha. Just about squeeze that in there using Z angles, and also using a bit of trigonometry as well. That's a right angle, so I can work out this angle here will be 90 minus alpha. Now if I now look at this bigger triangle, EC, well, the bit that goes down, there's no letter down there, but this triangle, that means that this angle at the top here is going to be 90 minus alpha. So this angle here is also angle alpha. Right, so now looking at this triangle here, ECF, this side here, which is adjacent to this angle with this hypotenuse of sine beta, this side here, E to F, is going to be cos alpha times sine beta, or sine beta, the hypotenuse, times by the cos of that. So let's put that in. That's what's going on here. So E to F is sine beta times by cos alpha. And this side here, so let's just put down that we've just worked out the length of that. This side here, F to C, that's going to be equal to the sine of alpha times by sine beta, or sine beta times by sine alpha. Okay, now what I'm going to do, I'm going to draw triangle AED out down here because there's too much working all in one place. And then you'll see we're pretty much done. So this is triangle AED. This angle here is the angle of beta and alpha. This is a right angle. The length of ED, well, ED is made up of two things. The top part down to F is, let's write it this way around, cos alpha sine beta, from there to there, and D to F is sine alpha cos beta. Now this side down here, A to D, well, A to B is cos alpha cos beta, but we need to take off, so we know the length from A to B, but we need to take off the length from D to B, which is FC, which is this. Yeah, so this is the length all the way from A to B, but I need to subtract the bit at the end because I don't want the bit from D to B, and that is sine alpha sine beta. Right, we're now ready to answer the question. Everything's there for us. So part A, the sine of that angle alpha plus beta is going to be equal to the opposite to that angle, which is d to e, divided by the hypotenuse, which is 1. I suppose I should put that on 1. Okay, now what was d to e? Well, d to e is going to be made up of these two bits, that and that added together, okay, which is the identity. So that's sine alpha cos beta plus cos alpha sine beta. So that's done. And then in part B, the cos of the angle alpha plus beta is equal to or equivalent to the adjacent, which is AD, over the hypotenuse, which is 1. Now A to D we've got, that's cos alpha cos beta minus that bit at the end we had to take off, sine alpha sine beta. So there we go, we've proved those identities. And as I said, you don't need to recreate that proof in exam, but it's there so you know where these things come from. Okay, so on this one we're not generating the identities from scratch like we did in the last one. We're just using the ones which we know already. Sine A plus minus B is equivalent to sine A cos B plus minus cos A sine B. So we know that already. We also know this already. Actually, in the last example, we just proved a plus, didn't we? So we're just using the plus. So let's take that out. So let's assume we don't know what the minus is, but that's all we know. That's what we've proved from the last one. So cos A cos B minus sine A sine B. Right, so let's assume that's all we know from that example 1 where we prove these and we don't know anything about the negative, and we're going to see if we can prove those. So what I'm going to do is, because I only know cos A plus B, I'm going to replace B with negative B into the cos addition formulae and see what I get. So cos A plus negative B will give me cos A cos negative B minus sine A sine negative B. So all I've done is replace the B with negative B. Well, the left hand side just becomes cos A minus B. You'll remember these identities, that if I've got the sine of negative theta, it's equivalent to negative of sine theta. And if I've got cos negative theta, that's cos theta. Let's draw that theta a little bit better. And I'm going to use those, right? So the cos of negative B can just be swapped out for cos B. And the sine of negative B, this bit, will become negative sine B. So that's going to affect that sign there, and that will become a plus. Plus sine A sine B. Okay, so we're done. We've proved our identity as required. And part B, so the tan of A plus B, well, tan is going to be sine A plus B over cos A plus B. So let's work that out. So we know the sine of A plus B. So sine A cos B plus cos A sine B all over cos A plus B, which would be cos A cos B minus sine A sine B. Now the trick with this one, which may not necessarily be obvious, is to divide the top and the bottom by cos A cos B. Yeah, may not necessarily be obvious. That's what you do. So if we do that, so the first term divided by cos A cos B, well, the cos B will cancel out, leaving me with sine A over cos A plus, and the second term, if I divide that by cos A cos B, the cos A will disappear, leaving me with sine B over cos B And then the bottom, again, dividing by cos A, cos B, well, that's just going to leave me with 1 minus, and dividing sine A, sine B by cos A, cos B will just leave me with tan A, tan B. So that basically be like sine A divided by cos A, which is just tan A, and then sine B divided by cos B, which is tan B. And then this very first bit here becomes tan A, so we have tan A plus tan B, tan A plus tan B all over 1 minus tan A tan B. There we go. So we've proved that identity as well. So here we've got this identity to prove. I'm going to start with, well, it doesn't matter too much which side I start with. I'm going to start with the left hand side. So I'm going to start with this cos A sine B minus sine A cos B. Okay, and whenever I see two fractions like that, what I want to do is put them together. So I'm going to times the first fraction top and bottom by cos B, and the second fraction I'm going to multiply the top and the bottom by sine B, so that they've got a common denominator. So I will have cos A cos B over sine B cos B, and then the second fraction will become sine A cos B over, I made a mistake there, sine B cos B. Right, so they're over the same denominator, so they can go together. So you've got cos A cos B minus sine A sine B over sine B cos B. Right, you should recognize this bit here as the addition formulae for cos A plus B. So we can stick that at the top, cos A plus B all over sine B cos B. Now you could have started instead with the right hand side, write the expansion of this, so you would have ended up with this, split the fraction up, yeah, and then you would have noticed, right, I've got things that cancel out. So you could have just as easily have gone from the right hand side to the left hand side, but we did it this way. So we did it this way. Right. Okay, so another one here. Given that that statement is true, express tan y in terms, express tan x in terms of tan y. Right, when I see something like this or this, I'm thinking to myself, let's use the addition formulae. So I've got two lots of sine x cos y plus cos x sine y on that side equals three lots of cos x cos y plus sine x sine y. Okay, so we want to get tan y on one side. So let's expand the brackets first, like this, plus 2 cos x sine y equals 3 we could use equivalent cos x cos y plus 3 sine x sine y. Now because I want tan, it would make sense to divide by cos, because if I got sine over cos, I can get tan. Now how am I going to get tan? Well, I need to divide by cos x, and that will cancel out all the cos x's and make these sine x's tan x, and I also need to divide by cos y, and then these cos y's will disappear, and then the sine y should become tan y's. So I'm going to divide through by cos x cos y, and the same on this side, cos x cos y. Okay, so if I do that, the first term is going to become 2 sine x over cos x. The second term will become 2 sine y over cos y. On the other side, the first term will just become 3, and then the second term will become 3 sine x sine y over cos x cos y. Right, that can be tidied up to give us 2 tan x plus 2 tan y equals 3 plus 3 tan x times by tan y. Okay, so express tan x in terms of tan y. So the last step is just to make tan x the subject. So let's move all the tan x's to one side. And move everything else to the other side. Let's factorize this side, so we get tan x as a outside the bracket. So you'll have 2 minus 3 tan y equals 3 minus 2 tan y. Last step, divide both sides by the bracket. So we'll end up with 3 minus 2 tan y over 2 minus 3 tan y as our final answer. Right, you should now be able to do exercise 7a on page 168 of the textbook.